almost course hai na. Okay, so we'll start off with our class. Okay, I'll start with my screen sharing. Okay. So I hope no one is there to join, because once I start with my presentation, then I won't be able to know who has been trying to join. Okay, 10 of you are there, so I'll start with my screen sharing. Okay. Okay, students, so what did we discuss yesterday? So yesterday we discussed on pixels, right? And pixel, we know it is the smallest unit to describe an image, right? And then we discussed on its relationships as well, like neighborhood and all. Then four-way connectivity, eight-way connectivity, adjacency. Then we discussed on distance functions as well, right? So am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So we discussed on distance functions, and finally we discussed on distance measures, right? So today we will again go through distance measures. Okay, we'll go through the topic on distance measures and some on relationship between pixels, and these two concepts are interrelated. Okay, but before that I would like to ask you, do you remember what has been taught yesterday, like function? So what did we discuss yesterday? That suppose we have an image here. Okay, we have an image here, and suppose f of xy, suppose f is the pixel here, and the pixel f consists of two coordinates, that is x and y. Okay, x and y. And then what is x? X is nothing but the row of a pixel. Yes, it is nothing but the row of the pixel, this. And then y is nothing but the column of pixel, right? So this is the column. Yes, so can you remember that? Yes guys, can you remember? Okay, then
Yes, ma'am.
okay, so then we spoke on some random pixels. Say I'm taking here as p and q, some random pixels. You can also take a, b, y, z, and all that. So I'm taking here as pq. So pq is any random pixel on the of this image. And then we discussed on distance function one by one, right? So what is distance function? I'm again reminding you that suppose here I am taking a 4 by 4 image. That is 4 by 4 means 4 rows, 4 columns. Okay. So suppose here is a 4 by 4 image, and we have been given 3 pixels, 3 particular pixels, say P, say Q, and Z. And these particular pixels have coordinates of x, y, s, t, and u, v respectively. Then what is the distance function? Here the distance function, suppose d, I'm considering d, will have the following properties. Suppose we have 3 properties over here. So the first property mentions that the distance between p and q is greater than or equals to 0. Okay, and if p and q are same, then the distance between p and q will be 0. Okay, the second property mentions that the distance between the pixels p and q is equals to the distance between q and p. Yes, so that is very obvious. The distance between these two pixels has to be the same. Yes, and the third property mentions that the distance between the pixels p and z, okay, is always less is always less than or equals to the addition of the distance between P and Q and the distance between the pixels Q and Z. Okay, so these three properties we discussed yesterday. So can you remember these? Yes, hopefully you can remember. Okay, so okay, so you can remember, so we can proceed to the next topic. So again, we discussed on distance measures, right? So distance measures, we have three types. So first is the Euclidean distance, then the second type is the city block distance, and the third type is chessboard distance, right? So all these three distance measures will have three different properties, or say formulas. Okay, so going on to Euclidean distance, I am continuing this because I'll be continuing with the same topic, so I'm giving you a follow-up. Okay, so here, what is Euclidean distance now? So suppose again we have a 4 by 4 image over here, and we have pixels P and Q, where coordinates for pixel P is x comma y and coordinates for pixel Q is s comma t respectively. So what is the, so we know x is row number and y is the column number. Yes, so x and y we are taking. Okay, so x and y. So what is x and what is y here? So x will be equals to 2 and y will be equals to also 2. Why? Because this is the second row and second column. Yes, one sec. So this is the second row, this is the second column. So this point, so this is what, this is p of xy is 2 comma 2. Yes, so I hope this concept is also clear, the coordinate system. Yes, and again q of s comma t, so q is in the fourth row and fourth column. So can you see this? So this pixel is s comma t, so fourth row and fourth column. So the pixel values, the coordinate values will be 4 comma 4. Okay, so till here you remember, right? So then what I'm trying to say here is, I'm talking about the Euclidean distance. Okay, so what is the Euclidean distance? So Euclidean distance is the minimum distance between P and Q, that is pixels P and Q. Okay, and what is this minimum distance? So simply the minimum distance is the distance of the straight line that is formed between the pixels P and Q. So how to calculate this straight line? Simply we use the Pythagoras theorem, and Pythagoras theorem means this: when a triangle is formed like this, in between these two we have to have a connection, right? We have to form a connection, so we are using the Pythagoras theorem, and we will calculate it by using this triangle, by completing this triangle like this. So Euclidean distance, we have a formula, we use the Pythagoras theorem like dE of PQ. Okay, and here dE indicates Euclidean distance. So dE equals to root over x minus s whole square plus y minus t whole square. Yes, and do you remember this formula? Do you remember yesterday we discussed? So x and s, these are, this is the row numbers. Okay, that is x is the row number for P, s is the row number for Q. Yes, and y minus t whole square, that is y is the column number for P pixel, t is the column number for Q pixel. Okay, and already we know the coordinate values, right? So x is 2 and minus s, that is 2 minus 4 whole square. Yes, plus y minus t whole square, that is y is 2 here, t is 4, so 2 minus 4 whole square. So we have to take the modulus function. Okay, why we are taking the modulus function here? Because we are not considering the sign over here. Okay, we are not considering the sign. Why? Because we are only talking about the pixel positions. Okay, we are talking about the pixel positions, and therefore we will only use the function, and when we are calculating the Euclidean distance between the points PQ by using the Pythagoras theorem, the answer we get is root over 8. Okay, so root over 8. So this is how you can calculate the Euclidean distance by using the Pythagoras theorem formula. So going on to the next topic today is city distance, that is city block distance. Okay, city block distance is the second type of distance measures. So the city block distance is indicated by this, that is d4 of p comma q. It is denoted by this equation, and the formula is d of d4 p comma q is mod of x minus s plus y minus t. Okay, so again consider the same image here, 4 by 4 image, where I'm taking p and q as my pixels with coordinates x, y and st respectively, and we already know the coordinate values 2, 2 and 4, 4. Okay, so what city block formula says is that this is the addition, right? So now how to calculate the city block distance? Okay, so we already know that the distance between any two adjacent pixels. Okay, what is adjacent? Tell me what is adjacent, guys. Hello. Hmm? One by one you tell. Okay, opposite value. Okay, fine. So you mean this? Suppose these two pixels are adjacent. This and this pixel adjacent. This and this. This and this. This and this. Yes. So are you trying to say that? Yes. Hmm? Guys?
Yes.
Yes, right? Okay. So you know adjacency. Okay, so always remember that the distance between any two adjacent pixel is always 1. Okay. So now suppose we want to calculate the city block distance over here. Suppose from this point to this point. Okay. So how we will calculate is, first we will calculate this distance, and then we will calculate this distance. And how we will calculate this distance is, suppose these two pixels, the distance is 1. Yes. Again, the distance between these two adjacent pixels is also 1. So 1 plus 1 is equals to 2. Okay. Then when you go from this pixel to this pixel, so these are adjacent pixels, so this distance is also 1. Again, from this pixel to this pixel, when you go, that is value is also 1. So total rounds off to 2, right? So total distance between these pixels will be 2 plus 2 equals to 4. Okay, so how? 1 plus 1 is 2, 1 plus 1 is 2, so total 2 plus 2 is equals to 4. So did you get the concept here, guys? So this is,
Yes.
yes, so this is the concept over here. Okay.
Ma'am,
Hmm. Hmm.
can't you directly use the formula that is
Yes.
D4PQ, that one formula? X
Yes.
equal to 2 and
Yeah, this formula you are talking about.
yes, ma'am.
Yeah, this is the, definitely this is the formula, but I'm doing this the conventional way. That is easily when you can see the image, like the image is in front of you, and suppose you want to calculate it directly, then you can go through this. Or else the see, the values are already given and you can place it over here. So only you can remember, for remembering purpose only I'm using this. Okay, so this is also easy, right? So this method is also easy, or you can directly keep these values in this formula, and then you get this straight away 4. Okay, so this is city block distance. Okay, so let us understand it more carefully here. What I'm trying to say is, suppose you have this image. Okay, take this image here. So tell me, So I'm trying, suppose, okay, first I'm taking this as my mid pixel, that is, this is the pixel in between at the 0th position. So what is the distance between this pixel and this pixel? Can you tell me? This to this, what is the distance?
1.
1. Fine. Okay, fine. So from this to this, hmm?
Same.
Same?
1 only.
1 only. Okay, from this to this,
Same.
Will be 1.
from here to here, 1, right? Okay, and from this to this,
Same.
Also 1.
same. Okay, so now you can guess the concept, so you know the concept now, right? So because these are all adjacent pixels. Okay, so now tell me, I want to calculate the distance from this pixel to this pixel. So how can we calculate it using this city block distance formula? Can you tell me? Or by
First,
looking at the image, how can
0,
we? Can I get
first 0 to 1 to 2.
First 0 to 1. Okay, then
1
from
to
0
2.
from 1 to 2. Okay, so what is the distance now? 1 plus 1 is
2.
2.
2.
Okay, so you got this concept, right? So this is all about city block distance. The same thing, we go on to the next concept. We have the chessboard distance. So chessboard distance is denoted by d8 of p comma q. Okay, so same thing, we are taking 4 by 4 image over here. We have p pixel and q pixel with coordinates x comma y, s comma 2, and you already know the values for these coordinates, that is 2 comma 2 and 4 comma 4. Okay, so now what we do is, this chessboard distance is given by the formula as maximum of x minus s and y minus t. Okay, so again, when we assume this image, okay, we consider this image. Suppose suppose, so you already know this, we know the values. So now we have, suppose we want to go from p to q. Okay, so how we will do this? First we will calculate, again we'll calculate this distance, and we'll calculate this distance, but this is different from the city block distance in the sense that after calculating the distance between the adjacent pixels, we will see which is having the maximum value, which is, which is having the maximum distance. Okay, so from p to q, when you go, see, this is 1 plus 1 2, again 1 plus 1 is 2. So the maximum of this, that is the chessboard distance for pq, is maximum of 2 comma 2. And what is maximum of 2 comma 2? It is 2 only. Yes, it is 2 only. Okay, one second. Okay, someone is waiting in the lobby. Okay, so let's go back to this. Sajib, could you enter? Yes? Yes, ma'am. No, ma'am. Sajib, I just admitted you. Okay. Okay, yes, ma'am. So, where were we? So, we were here. Okay, so maximum of 2 is 2 only. Yes? So, how to understand this concept well? Okay, let's take this image first. Okay, let's take this image first. And suppose this is the, sec. So suppose this is my middle pixel over here. Yes, so what I'm trying to say is, suppose again we know the distance between these two adjacent pixels is 1. This is also 1. This is also 1, and this is also 1. Okay, So tell me now how to calculate the distance from this pixel to this pixel. Hmm? Guys?
0 to 1,
Hmm.
1 to 2, 2 to 2.
Okay, don't take this. Okay, let me take a more farther pixel, this and this. So you'll go from here to here, here to here, right? And then again, yes, ma'am. Okay, and then from here to here, and then finally here to here. Okay, but these are only some random pixel values they have taken. Always remember that we don't have to see these values. Okay, this 2, 1, 2, we don't have to see that. Okay, only thing we have to check is what is the distance between two adjacent pixels. So from here to here, since we want to go from here to here, so from here first we will go from this 0 to 2. So this distance is 2, right? Again from this pixel to this, so distance is 1 plus 1, so 2. So here also the maximum value is 2 comma 2, that is it is 2. So did you get this concept now, guys?
Yes, ma'am.
Yes. Okay, easy, right? So in exam you'll get all these sums. Okay, so just you have to remember this, not exactly the image. You have to read the question well, then you have to draw the image, and then you have to plot this. Okay, then I'm giving you a problem here. Okay, the problem reads as, in the following arrangement of pixels, what is the value of the chessboard distance between the circled 2 points? That is, I'm asking the value of the chessboard distance between this one and this one. So guys, can you quickly
3.
calculate this? Okay, 3.
3.
3. Kenake pala?
1 to 0, 0 to 0, then
Hmm.
again 0 to 0, 0
Hmm.
to 1, then 1 to 0.
Okay, so you are saying
First
from
value will be 2
hmm.
and second will be 3. So maximum will be 3.
Okay, so you said from 1 to 0, 0 to 0 is the distance is 2. From 0 to 0, from 0 to 1 and 1 to 1, total distance is 3. And since we want to calculate the chessboard distance, so this is max of the both the distance, so 2 and 3, so you are taking the maximum as 3. So answer is 3, right? So did everyone get the answer as 3? Yes?
Yes, class.
Yes, ma'am. Okay, so see, so thing is that when you go through an image, when you see the image in front of you, you can definitely get the idea of how to calculate the coordinates and all. Okay, but when in exam you are asked a question like this, so what happens then? The teacher, or not the teacher, like the teacher, like the person who is evaluating the paper, they want to check whether you have the idea of the equations and formulas. Okay, so in a certain way in viva and all, you can directly say that this, so this the answer is 3. But in exam purpose, for exam purpose, you need the formulas to remember. Okay, you have to remember the formulas. I know you have understood the concept, but for this exam purpose only, you have to remember the formulas as well. Okay, so this is about the distance measures. That is, we have three types of distance measures. One is Euclidean, one is city block, and the last one is chessboard distance. Okay, then the next concept we go to is sampling and quantization. Okay, sampling and quantization. So let's go on to sampling first. So what we see here is, first, when we are talking about a digital image, okay, we talk about a digital image here. So first is digitizing an image. So how to digitize an image? We can digitize an image. For digitizing the image, we need to convert the continuous sensed data into digital form. Okay, continuous sensed data. And continuous sensed data here means the analog signal that we are talking about. And analog signal means the signals or the information that we get while capturing an image. Okay, by capturing when we capture an image through some lens or cameras or whatever system, then we get that signal as analog signal. Okay, so uh, okay, so analog signal you know now. What is digital image? You remember? Guys, what is
That
digital
consists of
image?
pixels
Is
Hmm?
taken by digital device.
by any
Okay,
pixel device.
okay, so you remember what is a digital image? Okay, so fine. So then so you know now what is digitizing an image. That is we are talking of a digital image, that is converting the analog signal to digital form. So this digitizing an image will also involve two processes. So that is, first is sampling and the other is quantization. Okay, so we'll go through sampling today only. So what is sampling? Okay, so sampling basically means digitizing of space. So here you can see a particular picture. Okay, so this is a particular picture. So this picture you can see. So when you digitize this particular pixel, we get the result as this corresponding picture as the digitized or the digital image. Okay, so conversion of this particular picture into digitized form is this. Okay, so if we further divide, suppose we are talking about this picture now. Okay, so when we further divide this picture in the form of pixels, okay, say take this suppose, and we consider this particular picture, suppose we consider this particular pixel here, then this is consisting of this particular line. Okay, you can see this line here. So this is a consist of particular line, and when we are talking about a particular line, or say when we talk about some lines, it consists of some infinite points in it. Okay, we can't see it through the naked eye, but there are infinite number of points or infinite number of points in this line. Okay, so if we want to accurately determine this particular line of the image, then it would contain some infinite number of pixels as well. Yes, so infinite line means infinite number of pixels, and an infinite number of pixels means what? We have to store that number of pixels in some memory. An infinite number of pixels means we will need infinite number of memories. Okay, so what I'm trying to say here is it is not possible to represent each pixel of the image, because when we want to represent each pixel, we'll be needing some infinite number of memory. So what we have to do is we have to convert a particular region, suppose, of this image into a single pixel. Okay, into a single pixel. So as we are converting this particular region into a single pixel, so this suppose will result into this. So it is doing it on its own. So the concept is that we have to convert this particular region into single pixel, and this will result in this. So suppose when we are considering a colored image, okay, when we consider a colored image, 50% or more of the pixel, that is the font from the colored image. So suppose when we are considering that if 50% or more percent of the pixel is colored, then we are coloring it. That is, suppose here we are talking of black. Okay, we are talking of black, or we are leaving it blank. Suppose this is blank. So you'll understand. I'll go through this concept again. It's a bit confusing. Okay, so what I'm trying to say is we can think that we can divide this pixel into some more number of pixels to increase the clarity of the image. Okay, and when we are dividing the pixels into more number of pixels, then definitely the image clarity will be increased, and eventually, but it will eventually increase the memory. That is, if you suppose divide a pixel into again subpixels, again those subpixels will try to capture some more memory. Okay, that is, more memory will be utilized to store that image. But yes, it can be done. We can store the image in the memory, but up to only a certain limit. Okay, so what I'm trying to say is in any part of an image there can be infinite number of points. So we can exactly store the analog image. I'm saying that this is the analog image. So this is analog, this is the digital image. So in any part of an analog image, there can be infinite number of points. So we can exactly store that image, for we need some infinite memory. And increasing the number of parts in a particular region of an image is split into, will increase the resolution. Okay, that is what I'm trying to say, is there can be infinite number of points in the memory, in the image, and which requires infinite memory, and increasing number of parts in a particular region of image is split into, which will increase the resolution. That is, however way you want to divide the pixels into subpixels, it will increase the resolution, but we won't have much space. And increasing in the number of pixels is called zooming. Okay, increasing in the number of pixels is zooming. So what I'm trying to say is, sampling means digitization of coordinate values. Okay, so sampling means digitization of coordinate values, that is the x. Suppose we take two axes, two coordinates, that is x and y, suppose. So x-axis and y-axis, and sampling is done prior to the quantization process. That is, quantization will come across after some time. So when you have quantization process, only you can go through the sampling process, and vice versa. So sampling and quantization both are dependent on each other. And sampling, it determines the, why we use sampling, because it determines the spatial resolution of the digitized image or the digital image. Okay, so when I'm talking about spatial resolution, what is spatial resolution? Anyone? Any idea about what is a spatial resolution? See, spatial resolution is a term which we refer to when we are considering the number of pixels which is used or which is utilized in construction of a digital image. Okay, that is, spatial resolution is nothing but it refers to the number of pixels or the total number of pixels which is utilized in construction of a digital image. That is, image having higher spatial resolution will be which are composed with a greater number of pixels. Okay, that is, image having higher spatial resolution are composed with a greater number of pixels than those having lower spatial resolution. Okay, so spatial resolution is the total number of pixels which is used in construction of a digital image. Okay, so then back to zooming. Okay, the sampling you understood now, so back to zooming. So zooming is nothing but increasing in number of parts or increasing in number of pixels of a what? Of a digital image. So that is zooming. Okay, so in zooming, what happens? Zooming is simply, it means enlarging a picture in a sense that the details in the image becomes more clear and visible. Okay, so when we enlarge a picture, and why we enlarge, suppose why we enlarge a picture, in order to get through the details more. Okay, we want to get an more insight into the quality of the image, suppose. So then we perform zooming. Zooming is nothing but what? You zoom an image, zooming of an image. Okay, that is, you are trying to enlarge the picture in order to get a more clear picture of the image. And zooming an image has a lot of applications, which ranges from zooming through a camera lens to zoom an image on the internet, and this is some example. Okay, so say you're taking an image of, I'm taking Einstein's image over here. So when you take this particular image and you want to apply zooming, what happens? This is the result. That is, you want to zoom this particular part of the image, so this is the result of zooming. Okay, then we have again two different steps in zooming. Okay, so the first step is, it includes zooming before taking a particular image. Okay, so in zooming while before taking a particular image is known as pre-processing zoom. That is, this involves some hardware and mechanical movement. Okay, and the second is to zoom an image once it has been captured. Okay, so this is done with using some various different algorithms in which we manipulate the pixels to zoom in the required portion. Okay, so we don't want to zoom the whole image. So just now I showed you the image for Einstein, right? So we wanted to zoom in some particular area on the face of Einstein, right? So zooming, that is the second step, is to manipulate the pixels to zoom in the required portion only, like whichever portion we want to zoom in. Okay, again we have two types of zoom, that is, one is optical zoom and one is digital zoom. So what is optical zoom? Optical zoom, this is achieved by using the movement of the lens of your camera. That is, optical zoom is actually a true zoom. They are telling it as a true zoom. That is, the result of the optical zoom is far better than that of a digital zoom. Okay, so in optical zoom, an image is magnified by the lens of the camera in such a way that the object in the image appears to be closer to the camera. Okay, so in optical zoom, the lens is physically extended to zoom or magnify an object. That is, you have seen those wedding photographers, right? So they have a lot, say they have a variety of this lens. Okay, if you have a digital camera, you can get the idea. So they can zoom in, zoom out using that particular special type of lens. So they are talking, this is about optical zoom. Okay, so that is, this optical zoom is achieved using movement of the lens of your camera. That is, physically you can move the lens of your camera and then you can zoom. So this is optical zoom. Then digital zoom is basically image processing within a camera. That is, during a digital zoom, the center of the image is magnified and the edges of the picture gets cropped out. Okay, so digital zoom means they are trying to focus on the center of the image. That is, they are trying to magnify or zoom the center of the image, and then the edges of the picture gets cropped out. See the Einstein picture, whichever I showed you just before. And due to the magnified center, it looks like that the object is closer to you. Yes. So this image, suppose I'm talking of this image. So what happens here? So when you want to zoom in a particular picture, so what is the digital zoom doing here? It is taking, suppose, the center of the image here. It is magnifying it, and the edges of the picture, it got cropped out. So edges, this got cropped out and we got a particular magnified image. So because of this magnified center, it looks like the object is closer to you. Okay, so during a digital zoom, what happens? The pixels gets expanded, but because of that, the quality of the image is also compromised. So could you see the Einstein image? When it was smaller, it was a bit better, but when you zoom the image, you could see a clearer picture of the image, but it was distorted. Yes, the image was a bit disturbed. That is, a lot of noise was present in the image. So when you try to zoom an image using this digital form, the picture, it gets expanded, but the quality is deteriorated. Okay, so this was about types of zoom, that is optical zoom and digital zoom, and next time we will discuss on quantization. Okay, so today we went through the process of sampling and its types. So next time we will go through quantization process. Okay, so till now, do you have any doubt regarding these topics? No ma'am. Okay, no ma'am. Okay, still if you have any doubt, just write it down. Okay, and you can ask me in the group. Okay, so that's all for today. So Nice. Okay, so how many of you are present? So all of you, I guess. Only Safikur is absent, I guess. Okay, I'll just take a screenshot here. Okay. Okay, so you can proceed for your next class. Okay, we'll see in the next. We'll meet up next time. Okay.
Thank you, ma'am.
Mm,
Okay, ma'am.
thank you.
Yeah,
Okay.
ma'am.
Okay.